Okay, people have been asking for another physics video. It's been like a year since I fucking made one. And what better way to do it than to do it on the layer that makes no physical sense whatsoever? Definitely not, so I can put forward in the title. Anyway.
A lot of the things you talked about don't make sense, I can't lie.
No, you see, they do.
Or,
Anyway.
or was it just Schrodinger's equation? That's
Oh, it's
it?
gonna get... Oh, I have jackhammers still. That's fine. We're playing jackhammers with 8-1 now. Anyway, I have... You know, if the people watching this video don't know, I am an astrophysics student at university, which means in 2 years I'm going to want to kill myself. So... that...
You're gonna want to kill yourself next year.
True. True. Lasagna is cooking there.
I am. Second year always sucks. Oh, no, it's tough. It's tough.
But anyway, point being is I know a little bit about physics, right? And like how stuff works. And recently, I have been learning about special relativity and quantum mechanics. This sounds scary. That's because it is. But I will make it digestible.
Really?
And not use all of the fucking jargon that my lecturers are using, where I'm like, what the fuck are you on about? When they're trying to explain, you can't go faster than the speed of light. We'll get to it. Anyway. What do you want to start with? Do we want to start with space, or do you want to save the space talk until we get to the space bit in 8.3?
It'd be cool to save it to space.
Okay, we'll save this. There's no bugs in fraud.
Oh.
There's no bugs in fraud. Anyway. So anyway, we'll start with the quantum mechanics. You ever heard of a guy called Schrodinger?
Yes.
Yeah.
I heard he has a cat.
Yeah. Apparently he's also a pedophile, according to my teacher.
Of course.
That was really cool to learn.
Oh, of course.
Anyway, that's not why we're here.
Okay.
This guy, he made an equation, right? You may have heard of it. Yeah, it's called Schrodinger's equation. Crazy, I know. Physicists really have creative names.
I know, right?
Their equations.
Like, oh, 4 equations. Ooh.
Real creative names. But anyway, Schrodinger, right? He was like, man, this doesn't make any sense. I'm gonna make it make sense. So, what he did was he made an equation, and it is usually an equation. It's something you make by just doing maths in general, right? You do some maths. Equation. Anyway, that's blue now because I picked up the red skull. Anyway, usually you get an equation from doing some maths, doing some complicated maths. Oh my god, never ask me to derive anything ever. But you do some maths and you get an equation. Not this time. This equation that he came up with has zero mathematical basis. It does not make any sense whatsoever. He pulled it out of thin air, made up some new thing he just called a wave function, which we'll get onto, doesn't make any sense, and it just works. It just works perfectly, by the way. Like, every experiment that has like used this equation has been like, huh, yeah, no, the equation works.
What the fuck?
Every single time. It just works. So whatever, right? So it's already fucked, right? Now, the equation, it's this is gonna be a big word, right? It's called a differential equation.
Ooh.
Sounds scary. All it means it's an equation that has the derivative of itself in it. Which, to explain what that is for people who, you know, maybe aren't used to like maths, that's like if you take something that is x squared, the derivative of that is 2x. And then the derivative of that would just be 2. Right? There you go. Crash course in derivatives. It gets way worse than that. But we're not going to go into that. The point being is the equation has the derivative of itself in it, as well as itself in it. And it equals itself. That's a very oversimplified, like massively oversimplified. But it's like close enough. Yeah, whatever. Nice checkpoint, Hakita. The checkpoint didn't work. What?
Oh, what the fuck?
Did I just miss it? How did I miss it?
There's no way you missed it.
Anyway, let's give us more time to talk about Schrodinger's fucking equation.
Yes,
We'll talk about his cat as well, because his cat's actually really funny.
Wait, what?
His cat there's some lore behind his cat.
What?
Anyway, so this equation doesn't make sense. Right. And it has this thing in it called a wave function. Would you believe it's the function of the wave?
Whoa.
I know. We're big stuff for Mr. Schrodinger here. Massive money from Schrodinger.
Money.
So anyway, this function, the way you solve it is you just kind of like throw in an equation. Oh, I must have missed that.
What?
I guess what you do is you just throw in an equation that when you derive it twice equals itself. So for example, like sine does this. When you derive sine twice, you get sine.
Oh.
So you just throw in something like that, and then you do some fucking shenanigans, and it just works. It just works. Now, if that sounds confusing to you, and you're like, wait, why does that work? Great question.
No one knows.
No one knows, but like, it just works. So.
Oh, this is so good. Oh, I'm loving this.
I'm stuck in the floor. Help, let me out. let me out.
Schrodinger did not like that.
Let me out.
Why?
Anyway, fraud has no bugs. Fraud has no bugs. So anyway, that's enough about Mr. fucking Schrodinger. Let's talk about something like.
What?
Let's talk about something kind of interesting, right? That's not just me crashing out. Actually, we could talk about Schrodinger's cat.
Yeah, I was about to say.
Everyone knows his cat, right? Like you put the cat in the box. Is the cat like it's both dead and alive?
Cool.
That's really stupid, right? Like oh, the cat can't be both dead and alive at the same time. That's dumb. Yeah, that's the point. Like the point of Schrodinger's cat is to point out how fucking stupid quantum mechanics is when you really think about it,
Yeah.
and how like little sense it actually makes.
Yeah.
That's the point. He's making fun of quantum mechanics, even though he like is like one of the pioneers of quantum. He's making fun of how like stupid it is. But the thing is it also just happens to be a really good explanation of quantum mechanics and how it works. So we just use it as one. Even though it's pointing out how stupid quantum mechanics is, we use it as an explanation for quantum mechanics. Because it is right.
Yeah, no, you explaining, like, I forget what it was. It's just like, you're not looking at the wall, and then you look at the wall and it's different.
Essentially.
Yeah.
Like, there's a very cool thing about quantum mechanics where theoretically, if all of the atoms lined up, or if you know, you got just there's a thing called quantum tunneling. We're not going to get into what that is because it's really, really, really confusing and complicated. Basically, all you need to know is there's a really, 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 really small chance that a solid thing just goes through another solid thing. Because technically, 99% of atoms is just nothing. So, if theoretically it lines up perfectly, they can just pass through each other like nothing happened. Which means there is an incredibly tiny chance of you just walking through a wall one day.
Damn.
Or just falling through the floor.
Damn.
But it's you have a better chance of like creating another universe by spitting into a jar of like soap. Yeah.
Mm.
That's a great analogy. I should use that one more.
When you become an astrophysicist,
Yeah.
you'll use that.
That's a great analogy. So anyway, the point being, right, is quantum mechanics is stupid and makes no sense. It doesn't make sense. How can something be both a particle and a wave at the same time? That doesn't make any sense. They are fundamentally different things that behave in different ways. But like, it works. And it keeps working. And it's currently the single most successful theory we have ever had of the universe ever. Because it just keeps working. So scientists are like, just see like how far this goes, I guess.
What?
The thing is like, okay, the problem is we know it's wrong. Like we know fundamentally it has to be wrong somewhere because it doesn't work with gravity. And gravity, I don't know if you've noticed, is a thing. Right.
Yes.
But it doesn't. Quantum mechanics does not work with gravity at all. There's quantum gravity, which is a whole different thing than gravity. I know. two different things.
Oh no.
That doesn't make sense. Why are they two different things? It's because it doesn't work.
What?
But
Huh?
yeah, it's because quantum physics, like every theory we have of everything, is wrong. Because we know nothing. There's a really good meme Hakita posted about like developing the forceful physics in fraud, and it's like, you know, 80%, 90%. Oh wow, this is going really well. The portals work so much better. And then at 95 and 99, it's just him going, fuck. That's unironically how actual physics happened.
Oh yeah.
For most of history, humans were like, wait, this makes so much sense. Like we discover Newton's laws of motion, and suddenly we can find energy in everything, and its force and its movement and where it's going to go. And everything's going great. Everything's working. We're learning so much about our world. Everything works. All of our equations work. For us on Earth. All of these equations that you learn in school, they work. They work perfectly. When you're talking about speeds you would find on Earth, and gravities you would find on Earth, and sizes you'd find, just like in everyday life, they work really, really well. The moment you stop doing that and you change it to like really fast speeds, really big things, really small things, stops working. And when physicists discovered this, they were like, "Ah!" And this happened like about 150 years ago. And that's when like relativity started being a thing. And then we were like, wow, this makes so much more sense. Finally, we can explain how planets orbit. And then people came along with quantum mechanics, because, and then turns out quantum mechanics and relativity don't agree with each other, but they both work. So physicists were like, "Fuck!" So that's currently where we are today, where we just keep on like discovering like more and more stuff about quantum mechanics, but we still fundamentally know it doesn't work with relativity. But relativity works. So something's wrong here, but we don't know what.
Because it all works.
It all works. That's the problem. They just only work for their reference frames. It's kind of fucked, honestly.
Yeah.
So anyway, we can talk about, maybe we can, since we're speaking about relativity anyway, I can mention some relativity shenanigans, right? Mm-hmm. Because I'm just saying relativity, but what actually is relativity?
It's so true, bestie.
Well, it's in the name, right? It sounds complicated, but it's just in the name, right? It's things that are relative to you. You know?
Oh.
Relativity is just the idea that things behave differently when they're in different reference frames. And you know, what is a reference frame, right? A reference frame could just be, you know, you standing still, you moving in a car, right? So okay, if you think about it like this, the best way I've heard someone describe it is this. If someone falls off of a building, right? They're falling, like if you're standing on the floor and you're looking at this guy fall from the building, from your perspective, he's, you know, accelerating towards you. He's falling. But if you think about it from the guy's perspective, with him falling, while he's floating and while he's falling, right? From his perspective, he's not actually moving. He's floating in midair, and the Earth is the thing accelerating towards him, which is very promptly about to smack him in the face and kill him. But you know, like the point is like two people in two different positions can see the same thing differently. So it's like if you're in a car, right, you'll hear the cars whizzing past you at a different noise to people standing still, because you're moving and they're standing still. That's basically all relativity is.
Oh.
It's just being like, okay, things happen differently in different situations, right? Problem. The big problem. The big question. Speed of light. Fucks everything up. It messes with everything, man. Because it's like, okay. So it's like, okay, so what if hypothetically there's a thing called a barn. It's like the something barn. I forget the name. But it's about a barn. And it's like this hypothetical problem of, okay, you're a farmer. You have a ladder. The ladder is 20 meters long. And your barn is only 10 meters long. Why'd you buy a 20-meter long ladder? Beyond me.
It's on sale.
Yeah. You can't, if you're that farmer standing still, and you're looking at the ladder, and you're looking at the barn, the ladder will not fit in the barn, because it's 20 meters long. However, according to relativity, if you were to say, hold the ladder, and theoretically run at the speed of light, right? Let's just say, hypothetically, you can run at the speed of light. And you're holding this ladder. Because of relativity, we then get this thing called length contraction. Basically, something that's moving really, really fast relative to something else looks smaller. Right?
Okay.
It's just that effectively what it is if you're standing still and something's moving at the speed of light, it looks smaller than it actually is.
Okay.
You can actually calculate this. Fun fact, the ladder would go from 20 meters long to about like 7. Anyway.
Okay.
Yeah. So, like you've heard of time dilation before, right?
I don't understand what it means.
Time dilation is essentially if you move really, really fast, like it fucks with how you perceive time. So like if let's say if you're moving like really, really fast, time will move slower for you than someone moving really, really slow.
Ah, okay.
It's the kind of thing where like people say like, oh, astronauts come back from space a little bit younger than you because they're moving so fast around the Earth.
Ah.
Imagine that cranked up to like 11 million. It's the same thing is true for like length. If you're moving really, really fast, the thing will appear smaller than if you're moving stationary for reasons that I don't understand. Anyway, point being, you have a 20 meter ladder, right? And from your perspective as the farmer, the ladder won't fit. Now, let's say you're still the farmer. You're standing still. And someone comes running with this ladder at the speed of light.
Ooh.
He's fucking fast. Suddenly, from the farmer's perspective, the ladder is less than 10 meters long because of length contraction, so the ladder can fit in the barn. So, from the farmer's perspective, the ladder can fit in the barn now, even though we know it's 20 meters, so it can't fit in the barn. But this is the interesting part. From the guy running's perspective, the ladder is still 20 meters.
Yeah.
Because the ladder's moving at the speed of light with him, right? He's holding the ladder, he's moving at the speed of light. So, from his perspective, the ladder's not moving. Right?
Yes.
The problem is the ladder, from his perspective, is 20 meters. But do you know what is moving from his perspective? The barn.
Ooh.
Correct. The barn, from his perspective, is racing towards him at the speed of light.
Ah.
Which means from his perspective,
That's small.
the barn is smaller.
Oh.
Yeah. Yeah, you get it, yeah.
Okay.
The barn is smaller from his perspective.
Oh no.
Which means that even though it fits from the farmer's perspective, it doesn't fit from the guy carrying the ladder's perspective. So who's right? That's the question. Which one of them is correct?
What?
Which one do you think is correct?
The dude running.
No, that was a trick question.
Fuck.
They're both right.
Oh, I was gonna say that.
They're both correct for their reference frame.
Shit. Okay.
That's the weird thing, right? It's like they're both correct, but they're also both wrong.
That was my. Okay,
But the thing is they're both correct in their reference frame
yeah.
and wrong in each other's reference frame, and then like vice versa, right?
Yeah.
So like they're both right in their frame and wrong in the other one's frame, and the other one's wrong in their frame and right in
Okay. Yeah.
just because they're going at the speed of light, and relativity just
Oh
goes
my God.
no. And the thing is like this is actually like verifiable. This is
What?
yeah.
What do you mean verify?
Like we have like seen like this happen experimentally.
Oh, okay.
Not with like ladders and barns,
No,
but
no.
with like particles and stuff and like light.
Yeah.
It's like super cool, and it's like it doesn't make sense when you think about it. But that's how it is. It doesn't make sense when you think about it because why is that? That's not how it works because we think from our perspective as a human being. It doesn't make sense. That's not how it works. What the fuck? But no, it works. And then the length contraction and time dilation are both a thing. So this means that like two events can happen at the same time for two people, but they'll like see it at different times.
Oh, it's different times.
Yeah. So it's like I think it was something like if you're in a rocket, right?
Yes.
And your rocket is stationary.
Yes.
There's another guy in a rocket, and his rocket is moving at the speed of light.
Okay.
And he gets like there's a flash of light at the front and the back of his rocket at the exact same time. Like these two flashes happen at the exact same time.
Oh.
From your perspective.
Where am I?
In the rocket that's not moving.
Okay.
From your perspective, these flashes happen at the same time. One at the front, one at the back.
Okay.
From his perspective, nope.
No.
Nope, not the same time.
Oh.
One had to happen earlier.
Oh.
The thing is like, either that has to be true, or you have to see them at different times, and he sees them at the same time.
Oh.
Both of those have to be true.
Oh.
Because relativity. Does that make sense? Not really.
No.
No, not really. Does it need to make sense? Also not really. Because this will never be useful in your daily life.
This is true.
You don't need to know this. But it does have some really interesting effects with, weirdly enough, particles.
Gotta love those guys.
Particles are really weird. So there's this crazy thing, right? It's called a muon. You don't need to know why it's called a muon. I don't know why it's called a muon. All you need to know is a muon is just a really fat electron. It's just a real heavy electron.
Boy.
That's all it is. It's just an electron that's really heavy. The thing about particles is there's a lot of them in our universe, right?
Yes.
We only know about, like, you might know protons, neutrons, and electrons. Because that's all that exists in our universe. Simplifying.
Okay.
That's all that exists in our universe, right? Because those are the only ones that are stable. There's like at least like 20 more or so that just aren't stable, but still exist, and a muon is one of them. It's just a really big electron. Now, I just told you muons are unstable, right?
Yes.
What does that mean?
Don't exist for a long time.
Yeah, no, that is actually what it means.
Nice.
They will like split apart into either just like some energy, which is just light. They'll radiate away, or they'll split into like smaller particles really quickly, like nanoseconds quickly. Like, and you can calculate this, right?
Oh.
So muons are formed just like when some like light hits the Earth's atmosphere or something like that. It's like they're formed in the Earth's atmosphere and they hit the surface. And you can detect this. And you can calculate, okay, there's this many muons that should hit the surface at this time, right? So I think it was something like they did an experiment on a mountain. The mountain was like 2,000 meters tall. And muons have a lifetime of, I believe, maybe like 2 microseconds.
Wow.
Very, very short lifespan, right? And because of the speed of the muon, right? The speed of the muon is just like a known thing. It's like 99.5% the speed of light or something silly. They're fast. And you can, using the speed, using the distance, you can calculate how much time it would take them to reach the floor from the top of that mountain. And if you know how much time it would take, you can roughly calculate how many should be left. So let's say you detect 100 at the top of the mountain. You calculate there should be 10 at the bottom. And then you measure how many are at the bottom. It's not 10.
Oh.
It's more like 90. Which is just like, that's a very like vague number.
Okay.
Right? Like it's way, way, way more than you would expect. The reason, and like you're probably wondering why we're on this tangent. We're going to circle back to it now. The reason is time dilation. I told you, muons move at 99.5% the speed of light, right?
Yes.
That means they're relativistic. And I told you, relativistic stuff in general, the speed of light, wonky stuff happens. Wonky things happen. So because they're moving at the speed of light, they experience time way slower than we do. 1 second for us is like a minute for them. Well, it's a lot. You can actually calculate like how long it is. I think it's like, I think that they experience time like 10 times slower than us or something.
Oh.
I don't know. We calculated it in class. You know what? Fuck it. If you want the equation, I believe it's literally like 1 over the root of 1 plus velocity squared over speed of light. And then you just put that in front of like the time, and you get like, okay, that's yeah. Or I think that's called the gamma factor, and it's what you multiply stuff by to be like, okay, it's this much longer, it's this much shorter, whatever. Anyway, point being, you can calculate this. Lasagna is, I don't know what you're doing. Anyway, so
the Switch 2 kept making noises. It's distracting.
Brilliant. So anyway, also fun fact, that's that blue thing's an actual real thing on Saturn. It's a storm. Anyway.
Oh.
It's a real thing.
I thought it'd be somewhere else on Saturn.
No,
I can't lie.
it's there. Anyway, back to the muon, right? So what happens is you calculate, right? Okay, these muons have frames.
I love frames.
I love frames.
This frame's so good.
So anyway, you calculate as like these muons have a relativistic thing of 10. It's called a gamma factor. They have a gamma factor of 10, which they actually do. And this means that they experience time 10 times slower than we do. So 1 second for us is 10 seconds for them. Which means that while we think like, oh, okay, it should take you, 1 second to reach the floor, from their perspective, from the muon's perspective, it takes them 10 seconds.
Reach the floor.
No, other way around.
What?
From our perspective, it would take them 10 seconds to reach the floor, and from their perspective, it's only 1.
What? So they... okay.
They experience time slower.
Slower?
So we experience 10 seconds happen.
Yes.
They only experience 1. So they experience time 10 times slower than we do. And the time it takes for us to see 10 seconds, they only see 1.
Oh!
Yeah.
Oh!
So, like, if you're holding a clock right now, and it ticks a minute, right?
Yeah.
If you were holding that same clock, moving at the speed of light, and you got someone to look at it and read the time, it would be moving, like, slower.
Oh!
Yeah.
Okay.
So the muons, the particles, they travel 10 times, they experience 10 times less time. They only experience 1 second at a time, so 10 seconds, whatever. So, instead of, having 10 seconds worth of decay, like you'd think, it's only 1 second. Because they've only experienced 1 second of time.
Damn.
So way, way more particles actually reach the floor than you'd think.
Ah.
And this is like an actual, verifiable, calculated thing that we did. There was an experiment done that proved that, yes, this is real. This is actually how it works.
Damn.
This is a thing that happens. A real, undisputable thing. Which is like, that's why I've been saying this whole time. Like, it doesn't make sense. It doesn't sound like it should be real. No, it's real. We have proof that it's real. Also, another thing that kind of proves okay. There's a really cool story about like why we even bothered like learning all this. So the planets, right? The planets that we just saw in the last level. Hey, you can see most of them with just like the naked eye, right? You can see up to, I believe, Saturn with just the naked eye. Or you can see Uranus with the naked eye.
Ooh.
Fun fact, back when the Divine Comedy was written, the reason it only goes up to Saturn in this game is because it's based on Divine Comedy, right? And back when I couldn't see anything, I still don't like this boss fight.
Yeah.
The reason in the Divine Comedy and in this game, you don't see Uranus and Neptune is because they weren't discovered at the time. Just straight up.
That's fair enough.
Which is cool. But, so anyway. When we discovered Uranus, they did the maths, and they were like, wait a minute. This orbit doesn't make any sense at all, whatsoever. We don't understand why it's orbiting like this. So someone was like, okay, guys, there has to be a reasonable explanation for this. What if there's a planet behind Uranus pulling on it? Right? That made sense. That made sense. Okay, there's a planet pulling on Uranus from behind it. Okay, sure. Let's try finding that planet. They got lucky. They found Neptune. right? They found Neptune. Neptune exists. Neptune was, in fact, pulling on Uranus. So their explanation made sense to them. They were like, okay, no, that makes sense. Then they noticed Mercury's orbit. Didn't make sense. Didn't make no sense. So they tried the exact same logic. They were like, okay, if there was a planet pulling on Uranus, there must have been one pulling on Mercury. So then they go looking for this planet. They called it Vulcan.
Oh.
And they were looking for a planet between Mercury and the Sun. Obviously, there's nothing there, right?
Yeah.
There is no planet between Mercury and the Sun. They were wrong. So, how do we explain Mercury's orbit? It doesn't make sense. Like, physics, I don't know what level I'm going to play. I'm going to go play P2 lol.
Oh, okay. I thought you were going to do 8-3 again. I can't lie.
Nah.
Alright.
So anyway, so we're trying to explain Mercury's orbit, right?
Yes.
Because physics doesn't explain it. At least at the time. It didn't explain it. It didn't work.
It's okay.
It just didn't work. It was wrong.
Okay.
So that's when Einstein's like, oh, relativity.
Oh.
He like first brings up the idea of relativity, right? And it's like, and it works, right? That's the thing. It works. It works really well. It works great. It works amazing for like everything in space, for everything at light speed, for everything with a shitload of gravity. It works. It's great. Doesn't work for quantum. That's the problem. That's the biggest fundamental problem. If you can figure out like how to get gravity to work with both quantum and relativistic physics in one equation, you will be like one of the most famous scientists of all time.
Oh.
Like it is like the holy grail of physics right now. Like if you can do that, yeah, GG, all the Nobel prizes.
All the Nobel Prizes.
All of the Nobel prizes. That's crazy.
The...
No, I'm not. We're P-rank this level.
I was about to... Can I mention...
What?
I'm gonna talk about eugenics and stuff.
Fun fact. The most common word in like Nobel Prize winners like works is just straight up eugenics.
Yeah.
Because would you believe a bunch of like middle-aged white guys who like had a massive case of I'm better than everyone syndrome.
All went to like very good universities.
All of them went to universities in like the 1920s.
Yep.
Pretty racist guys.
Wow.
It's crazy.
I had to learn about this in my lecture.
Yeah.
It was interesting.
But anyway, point B. Physics. It doesn't make any sense. But it also does kind of, but it also doesn't.
The quantum I just can't get over.
Quantum physics is the biggest. Like relativity, if you think about it for long enough, you can understand it.
Yeah.
Like you know, you can get it. It's like okay. If you move really fast, things get slower and things get smaller. Sure, whatever. Quantum mechanics is just the particle's a wave sometimes. Sometimes it's a particle.
Exactly.
Sometimes it's kind of like both. We don't really know what's going on. Anyway, you know what? Speaking of like dumb bullshit, we don't really know what's going on. Hey, you ever heard of like you ever heard of this crazy thing, right? Called the conservation of energy. Like this little thing that basically says, hey, you can't make any energy, you can't break any energy.
Oh my god.
Right?
Yeah.
Conservation of energy. It's a thing you get. You know, like everyone knows this is a thing, right? Like you just kind of know it's a thing. That was a good rail cannon. I like that one. You know, you just know from like being a kid. You're like, okay, you can't do this. You can't make energy. You can't break energy. LOL. Yeah, you can. Kind of. You can kind of do it. So, we're gonna introduce a new thing right here. Right, Heisenberg, that guy from Breaking Bad. Turns out it's actually a German scientist who was leading the Nazis' version of the Manhattan Project, which was trying to make a nuke. So, you know, it's just a Nazi.
Okay.
He's actually a very controversial figure because a lot of people wonder like whether he purposefully sabotaged the Nazis' atomic program, or whether he was just bad at his job. Like, there's a lot of debate around that.
Okay.
But anyway, we're not going to get into that. Point being, is this guy has a principle. It's called Heisenberg's uncertainty principle.
What?
And it means that, essentially, there's two versions. There's one where you can't know both a particle's momentum and its position. Technically, you can only know it to the Planck's constant, but for the principle of this video, you cannot know both a particle's momentum and a particle's position. You can't know both at the same time, you just can't.
Okay.
And the bit we're interested in is you can't know both a particle's energy and, like, the time it's around for. Like, you cannot know both energy and time in a particle. This is very, very interesting. Because it means over really, really, really small periods of time, like really small, like inconceivably small amounts of time, you don't know how much energy that thing has. It could have as much as it feels like. It could have as little as it feels like. It could change. As long as it goes back to being, you know, something that makes sense by the time you know how much time there is. Like, okay. So, there's this thing. There's a thing, right? Where over, like, a really, really, really small period of time, like, so tiny it may as well not even count, a particle could, say, just spawn a new particle out of thin air, creating energy, then absorb that particle, which means that our starting particle has more energy from thin air. It has created energy. And according to the conservation of energy, that's not possible. You can't do that. Well, you know, you either don't know whether or not it has actually gained energy. Like, you don't know that. If you know how much time it's been, you don't actually know whether it's gained energy or not. And if you don't know how much time it's been, well, who's to say that something didn't change its energy? You don't know. You don't know how much time's passed. So the whole idea is basically, lol, lamau.
It created energy.
It can do that. It's just they're just physicists realizing, like, wait a minute. Oh, fuck. It can do that. Oh, we have to, oh. That's essentially all quantum mechanics. It's just physicists going, ah, fuck, we didn't think of that. It's just that has zero, by the way, this has zero practical use for anything ever. It's literally just it's just there because someone realized, wait a minute, this says you can make energy out of thin air, and someone went, fuck, Lamau, you right. And then they were like, do we need to worry about that? And then someone else was like, yeah, probably not. You don't need to worry about it, it's fine. Like, this is stuff that you don't need to worry about. It's just like, hey, conservation of energy is bullshit sometimes, lol.
Lol.
Anyway, physics yap over for the next, like, year.
Yeah.
Maybe. Unless something interesting comes up, who knows, it might happen next week.
Maybe?
No.
Oh.